closely at the mortar binding these ancient stones. Some of these structures have stood for over 2,000 years, braving monsoons and intense heat. To achieve that kind of permanence today, civil engineers rely on a specific code, Indian Standard 712-1984, specifically Section 3.1, which dictates exactly which type of building lime goes into which part of a structure. India's vast geological diversity produces a wide variety of limestones. The intricate, load-bearing columns you see here survive because the builders understood the specific chemical properties of the lime they were using, a practice the modern code standardizes. The code defines 6 distinct classes of building lime, labeled simply A, B, C, D, E, and F. If you are preparing for a licensing exam, your first instinct might be to memorize this list in straight alphabetical order, but doing so creates a cognitive trap. Classes C, D, and F all list finishing coat in their applications, while classes B and E both handle masonry mortars. Rote memorization quickly collapses into confusion. The alphabet is a bureaucratic filing system, not an engineering framework. To master IS 712, we have to discard the letters and look at the underlying chemistry. Every classification in this code is driven by 2 chemical variables: hydralicity, meaning the presence of silica and alumina impurities, and magnesium content, which indicates dolomite. This diagram shows a better way to map the code. We can split the entire IS 712 classification into 3 logical chemistry-based branches. The first branch is the hydraulic spectrum. These are limes that rely on clay and silica impurities to develop their strength. The second branch is the dolomitic family, defined by high levels of magnesium. And the third branch is the Concar outlier, a naturally occurring anomaly in the Indian geological landscape. By categorizing the limes through these 3 chemical branches, we can link each class directly to its intended structural application. Let's examine the hydraulic spectrum. This branch operates on a sliding scale of strength, moving from highly impure and strong at the top to highly pure and weak at the bottom. At the very top sits Class A, the eminently hydraulic lime. The IS code explicitly assigns Class A for structural purposes. Because it contains the highest level of reactive silica and alumina, it possesses the maximum load-bearing capacity of any lime. Moving down the spectrum, we find Class B, the semi-hydraulic lime. With moderate impurities, its strength is reduced but still functional. The code assigns Class B to mid-tier structural roles: masonry mortars, lime concrete, and plaster undercoats. At the bottom of the spectrum is Class C, commonly known as fat lime. Fat lime has virtually 0 hydralicity. It is essentially pure calcium. Lacking the chemical components for compressive strength, it is strictly relegated to superficial applications, the finishing coat in plastering and whitewashing. However, board exams frequently test a specific caveat. Class C can be used for masonry mortar, but only if pozzolanic materials are manually added to compensate for its lack of natural silica. The rule for the hydraulic branch is simple. The higher the silica impurity, the heavier the structural load it can carry. The purer the lime, the better it serves as a visual finish. Now we shift focus to the second branch of the tree, the dolomitic limes, characterized by their significant magnesium content. This branch starts with Class D, magnesium or dolomitic lime. The IS code assigns Class D for the finishing coat in plastering and whitewashing. Functionally, it operates exactly like Class C from the hydraulic spectrum. But right below it is Class F, silicious dolomitic lime. The code dictates that Class F is used for both the undercoat and the finishing coat of plaster. Pay attention to the chemistry. The addition of silica to the dolomite gives Class F the compressive strength required to act as a supportive undercoat. Within the dolomitic family, the term silicious is the technical distinction between a pure finishing coat and a dual-purpose undercoat system. Recognizing that specific chemical addition is the most effective way to differentiate between these 2 magnesium-heavy classes. Our final branch covers an anomaly. These are limes derived from natural calcareous nodules found in the soil, rather than mined from standard limestone quarries. This is Class E, Concar lime. The code restricts its use exclusively to masonry mortars. Beyond the classifications, we have to look at how these materials are physically processed. This photograph shows workers managing a traditional lime-burning kiln, where extreme heat converts raw limestone into reactive lime. Once processed, building limes are typically supplied to job sites in one of two states: as highly reactive quicklime, straight from the kiln, or as pre-slaked, stable hydrated lime. This leads us to a crucial detail hidden in Section 3.1, Note 1 of the Code, a detail that reliably trips up licensing candidates. The code contains a strict exception. Class A, the eminently hydraulic lime, and Class E, the concar lime, are legally prohibited from being supplied as quicklime. The underlying engineering reasoning here is practical. Because of their heavy clay and silica impurities, attempting to slake these specific limes on a job site yields highly unpredictable results. They must be hydrated at the factory. Minimizing this specific supply constraint for A&E is a guaranteed way to secure points on Construction Material Board exams. Now, let's lock in this mental model by compressing our three chemical branches into a fast recall matrix. For strict structural purposes, we check the highest point of the hydraulic spectrum. Only Class A qualifies. For masonry mortars, we look at the mid-tier options, Class B, and our outlier, Class E. And remember, Class C joins this row only if pozzolana is added. For plastering undercoats, we rely on the moderate strength of Classes B and F, but for the purely aesthetic finishing coats, we drop down to the pure limes, C, D, and F. Visually mapping the overlapping applications shows that functional chemistry is the most reliable way to apply the specifications of IS 712. Let's test this framework in a high-pressure scenario. Consider this typical exam question. Which of the following dolomitic limes is specified by IS 712 for both undercoat and finishing? Apply our keyword isolation technique. The prompt specifies a dolomitic lime used for undercoat and finishing. The word dolomitic immediately filters out the entire hydraulic branch. Because it requires strength for an undercoat, we bypass the pure Class D, leaving the silicious Class F as the only logical answer. Combine this matrix with the golden hydration rule, remembering that Classes A and E must exclusively be supplied in hydrated form, and you have mapped the entire system. Treating IS 712-1984 as a rigid chemical taxonomy rather than an arbitrary alphabetical list transforms rote memorization into bulletproof engineering logic.